Great to have you here. And with me, I have Akshat and Colin, and on the line, David Lepzelter. One of the great things about working at InterSystems is working with really smart people, and these are the developers that work on IntegratedML day in and day out, fixing bugs and making new features, and they're going to talk about new features that are coming out kind of very soon. We have an early access program that we'll talk about. So anyways. Thought that was working. There we go. Okay, so the overall agenda, I'm going to just kind of recap what IntegratedML is, just in case you don't know, and it's the first time you're hearing about it. We have some new feature that's coming out about kind of managing the timing of training in one of our providers, one of the engines. And we're going to talk about something that will be coming out in the future. It's in the hopper. About doing explanations and getting explanations from your models. And also a new feature, time series modeling, so doing forecasting with IntegratedML. It's a feature that Colin's been working on. He's going to show us how it works. It's some new syntax and some new capabilities. And we have an early access program for it, so do that. And then we'll just wrap up after that. So what is IntegratedML? So IntegratedML, as it says right there, brings automated machine learning, or AutoML, to SQL developers, and it augments the productivity and reach of data scientists. So it's really about just kind of smoothing things over. It's not automating everything about machine learning. It's a very straightforward kind of tabular ML. But as you can see, the syntax is really straightforward. It's all SQL, so you can do everything you need to do anytime you can get a SQL connection. So that's really nice. And then we have different engines underneath that do the machine learning a little bit differently. In one case, the default one is our own AutoML provider. It uses underneath some TensorFlow, scikit-learn. It's built using embedded Python. We also have a partnership with DataRobot. If you have a DataRobot account, that machine learning will get done on their cloud service, or you can actually install that on-premise. And then we also have an H2O AutoML engine. That's a very nice open source AutoML engine that's been around for a while and just performs really well. So you can choose and mix and match depending on what you're doing. Oops. Oh, yeah, so I forgot that I put this in there. So I'm going to go back over those. These are the three providers that I just went over. This shows in a little more detail of what they're doing and what the other ones are not doing. So we have embedded Python. That's how our built-in one has been implemented. H2O uses our Java gateway, and it pulls data using JDBC underneath. And then DataRobot has a REST API that we're using to call DataRobot. So that just kind of shows off some of the flexibility of what we can do. And how we do things. InterSystems Iris is super flexible. Next. Okay. And really, the differentiators it's really the simplest syntax. If you compare doing machine learning with, there are some other in-database machine learning kind of toolkits. Oracle has had stuff for a long time in kind of stored procedures. Google BigQuery is also something that has built-in ML. But our syntax is just so much more elegant. It's just really easy to use. And that's one of the great things about it. We have deep integration with the SQL engine. So we treat prediction work natively. We can manage when we're doing things in batch or when we do it row by row. So that makes it very performant. And you just don't have to worry about how you're getting your predictions. You just treat it like SQL, and our SQL engine treats it like anything else. And we've just packaged everything together. So it's a feature of InterSystems Iris that just gets installed when you install it. We have separated out kits, so some people don't want a huge install, which is the way that it was packaged and delivered, so we have separate kits. So you have one without ML or one with ML, depending on what you need for what you're installing. And then things, although it's great to have all of these options and different providers, I wanted to lay out a little bit of the kind of differences between those different providers, where they show up, and how that relates to what we're showing you today. So, broad terms, our AutoML is kind of the easiest to use. There's really no parameters for it. It just kind of does everything on its own. H2O, you can give it some more parameters, so it's a little bit more like you can customize it. And DataRobot, similar. The configurability, though, with H2O is really high. You can actually tune the engine to choose some algorithms and not others. So, for example, you may not want to train neural networks. You may only want to look at tree-based models, random forest types of things, and you can tell H2O what to do, which algorithms to try and which not to try. If you really need the best and pay for it, DataRobot has amazing resources, and their engine is just very, very well tested. It's just a huge juggernaut of cloud resources that you can throw at a machine learning problem. And they also have a wonderful user interface where they give you all sorts of way to kind of inspect your model and get to really understand it better. But it's a separate license, and so that's the drawback there. So we're also rolling out Cloud SQL and with IntegratedML. So as a cloud service, we've started out with just the H2O provider, and there's no choice to change that. That will change in the future. And then time series modeling that we're talking about now initially is going to be rolled out for just the InterSystems AutoML provider and our DataRobot provider. And we'll add H2O in the end. So with that, that's just kind of overview. I'm going to let Akshat take over and talk a little bit more about some new features in Iris.
Thank you. Am I audible? Okay, sweet. So Tom touched upon IntegratedML as a product as a whole. So think of that as an umbrella. And then there are 3 providers under that, right? AutoML, H2O, and DataRobot. So I want to talk about the configurability aspect of these providers, and specifically of AutoML. So think of that as knobs that the user can tune to sort of tell the model selection process that as you as a data owner understand things that the model selection does not. So you want to guide that process to come up with the most, the best kind of trained model that it can, given your expertise. Now, I want to talk about one knob in particular called training modes. So naturally, there are a bunch of users, and they fall at different aspects of this, different points on the spectrum. At one end, we have people who care about accuracy a lot, right? So you have a medical data set, and there is no way that you can afford to have a margin of error. You want to minimize the number of false positives, false negatives, and you don't care how long it takes to train your model. All you want is the best possible model. For that, we have score mode. On the opposite end of the spectrum, we have time mode, which is basically someone who's, let's say, experimenting with their data for the first time. You don't know how long it may take. It's a massive data set. And you want to say, take 2 hours, train some kind of model, and give me back a reasonable answer. And then you can work with the model thereon to pick one of the other modes. So that's the opposite end of the spectrum with time mode. And somewhere in the middle is balance mode, which takes into account both these factors. Now, we've looked at a bunch of providers available outside, and I'm particularly interested in time mode of the 3 because we've seen that not a lot of people provide that mode, and the few providers that do have it, the way that it works currently is, let's say you say, take my data, here are 2 hours, give me back a model. And the clock's counting down, it hits 2 hours, and you don't have a model trained yet. So what do? They shelf all the work that they've done so far, scrap it all, and you have to start from scratch with a higher time threshold. That seems to be a bit of a waste of work, right? Especially if you've let it train for a long time. And so what we've done with time mode is we've said, you can specify the max amount of time, but we'll use that as a sort of a guideline, a soft threshold. And what we'll try to do is we'll try to complete it within 2 hours, give you as reasonable of a model as possible. And if not, if it takes 5 minutes more or 10 minutes more, we'll keep going and try to give you the next best model. But you always have the option of doing a manual abort in the middle in case it exceeds your time expectations. So that's the first hyperparameter within this knob. That's the max time. The second one is the model score. So let's say that you have no idea what kind of results this data set is capable of producing. But you say, I need at least an 80% classification accuracy, otherwise this is all useless to me. So you'd specify that as the desired model score. And at that point, we say, that's more of a hard threshold. So we evaluate a number of models, and if we realize that none of those is going to match your requirements, then we abort the process right there. But this happens much earlier on in the pipeline. So the training score, the max time kicks in towards the end of the pipeline, whereas the score kicks in towards the start. And so we don't waste too much time evaluating whether or not we can give you those models. So I think most of you might have a decent idea of who would like to use, for what kind of data sets you'd like to use score mode or time mode. But I just wanted to run a few benchmarks that we did by you, and just to illustrate the different scenarios where you might want to use one over the other. So this is a popular data set called the campaign data set. It's a binary classification problem. The output is a response variable saying 1 or 0. And the important thing is on the left, you can see the amount of time taken by both the modes. And clearly, score mode is taken thrice as much as time mode. So that's a big win for time, right? Because you're saving all of that time. But at the same time, somehow, magically, it's managed to achieve almost the same score as time mode. Right? Score and time, I think, both got 80.2% of an accuracy on this classification problem. And so how did that happen? One of the tricks that training modes uses is it evaluates. So we have a bunch of models that we train our data on. And some of those models are way more complex and time-consuming than the other ones. And so what time mode does is it sort of uses the simpler, more easily generalizable models at the cost of not picking up certain nuances in your data. And many times, like in this case, it works pretty well. Because you can see score mode would have tried out the more complex model, and yet it picked the same data, the same model as time mode. So in some cases, time mode and score mode give you the same accuracy. However, so this is the poker data set. This is, again, a classification problem. If you were to randomly guess an answer on this data set, you'd get it right 1 out of 6 times, which explains the slightly low scores here. But a random guess would be way down at like 12%, 15%. And here, again, you can see that time mode has taken probably half the amount of time as score mode, which, again, is a pretty good achievement. But the score, there is a significant difference, about 10%. And so depending on where on that spectrum your interests lie, that could either be a lot, or you might think that a gain of 50% in the training time is a fair enough trade-off for a 10% drop in accuracy. So that basically describes the training modes that we have and the way that you can use them to sort of play around with your data initially if you don't want to spend too much time, and then probably dive into score mode and if you want better looking models. The next thing I want to talk about is explanations that our data scientist, David Lepzelter, has worked on. It's pretty cool, according to me. He's not here, but he's on call, so if you guys have questions, then you can talk to him later. So I want to touch upon what explainability means in the context of machine learning and why it might be important. So let's say you have your data set, you've trained it, now you have a trained model, and it gave you a validation accuracy of 99.9%. You were super happy with it, you deployed it, you started prescribing medicines to patients, and a few months in, their skin started turning blue and their hands fell off and weird things started happening. And you went back to your model and you thought that it was 99.9% accurate, but was it? And clearly it wasn't. And to answer why that wasn't the case, you could use something like explainers. So the one that we use is called the SHAP explainer, which is a popular Python explainer, or popular explainer implemented in Python as well, and it's based on the Shapley concept. And what it does is essentially tells you these were the columns that were the most important ones with respect to this data set. And so if that does not align with your intuitive sense of the data, then you know that there's something wrong going on there. I won't get into the theory of how SHAP works, but I'll explain these two plots, and hopefully you'll get an idea of what it's doing. So unintuitively, we'll go from right to left, and we have this thing is called a local interpretability plot. And what it's doing is it's essentially each of these vectors is an importance vector. It's explaining what each column has, what kind of impact each column has on a given prediction. So let's say we're trying to predict a regression problem like predicting house prices. And let's say the mean house price in our data set is $100,000, I wish. And so let's say that is the expected value here. So $100,000 is what the mean price is. And then we start introducing each column. And every column corresponds to a feature, say the locality, the number of bedrooms, bathrooms, etc. And then we see the impact each feature has on the final prediction. And you sum up all of those predictions plus the mean value, and that gives you the final predicted output, which is up there. As a result, this kind of plot tells you what one data point, how one data point has been impacted by various columns. So that's one patient, one whatever, right? What if you wanted to do this for your entire data set? And that's where the bee swarm plot on the left comes in. So each of these vectors, if you were to, let's say, map the red vector as one point there, and you did that for all of the million data points you had in your data set, and you plotted them all, that's what you'd get. And as you can guess, the larger the spread, the more impactful, or the more variance that the column models in your data set. And the red and blue, in this case, just explain the direction, up or down, that it has an influence on that data point. So these graphs have been generated using the code provided on the GitHub link there, which I can share with you later. But what AutoML does is, true to our SQL nature, we have a pretty simple select statement, select, explain, predict, the model that you've trained, and then from the table that you want to explain. And that's all you need, and then you get a bunch of explanations for all of the points that you specified in the from clause. Where are we with this in terms of development? Development's complete. We're almost through with testing. It's in beta, and it should be released sometime this year. And if you have any questions, then either I or David can talk to you about this afterwards. Sure.
Well, you mentioned that IntegratedML is available with Iris today.
Yes, so IntegratedML is available. That contains the creating a model, training, predicting, all of those features. And then explainability is also a part of IML that will be shipped out soon.
So you're adding explainability in the future, right?
Correct.
Okay.
Yeah.
So what is this like? So you're going to have syntax like this, explain, predict, and then you're going to get like new capabilities for these queries?
Correct. So we have SQL, custom SQL keywords. So
okay, but you extend the SQL.
Exactly. We extend our own SQL, which in turn is an extension of SQL. And that's it. Colin will talk to you about time series forecasting.
All right. Thanks. Hey guys, my name's Colin. It sounds like the speaker's working well. I'll be showing you our new time-aware forecasting feature in IntegratedML. We'll start by reviewing traditional machine learning. In traditional machine learning setting, we utilize models like MLPs and random forests to make predictions across a row of data. If you take a look at the table here, you would look at like row 1, and you would use the feature petal length in row 1 and petal width in row 1 to make the prediction of the flower's identification, setosa, all across a single row. This type of modeling is not well suited for sequential data. It is difficult to use data from, say, rows 1 and 2 to make a prediction about the third row. It is possible. You can use duplication or lag features, but it's far from optimal. So what we choose to do instead is sequential modeling is a time series model. So some popular examples of algorithms here are Prophet, ARIMA. We have recurrent neural networks as well. These models allow us to make predictions down each prediction column, or as I'll call them at points in this presentation, channels. And as we can see in the table, we will be using data from the first 4 rows here to make predictions down and populate 2 new rows of predictions. So this type of modeling will allow us to model sequential data easily and without replication or lag, which can save a bit on memory. And in addition, most time series models utilize a thing called seasonality. Sorry. So if you think about, on this chart we have ice cream sales on the right there. If you think about ice cream sales, you would expect to sell more ice cream in the summer and less in the winter. You might also expect to sell more on the weekend than a Wednesday perhaps. So that's the idea of seasonality, and most time series models will utilize that heavily to increase their predictive power. So to summarize, time series modeling is great for sequential time or date stamped data from one or many sources. This type of data is vital in many fields, including forecasting of weather, public health, and perhaps supply chain demands. We have a few more here on the slide. There's a couple limitations that we need to be aware of. Time series modeling doesn't generalize as well to new data as traditional machine learning will. You often will require some amount of recalibration or retraining when faced with a new source of data. We also need to keep in mind that the forecasting distance is not unlimited. The amount of training data you provide the model will influence how far into the future you can predict. As you can imagine, if you have 1 year of weekly sales data, you wouldn't expect to be able to predict your sales in 10 years. That would be a bit optimistic. And the packages that support time series modeling will place some restrictions on you in situations like that. In InterSystems Iris, we are planning to release and support time series modeling for 2 providers at first, AutoML and DataRobot, with support for H2O coming in the near future. As with all our IntegratedML products, to utilize AutoML time series, a user simply has to submit a simple couple of queries, create the model query and a train the model query, and everything else will happen under the hood, behind the curtain. A lot happens under the hood. We convert the data to a stacked format, we make the necessary transformations, and make some determinations about how to best handle things like missing data and the frequency of your date time information. Then we leverage the AutoTS library, which will return a powerful forecasting model. This library includes automatic seasonality detection, creates ensembles of popular models with various parameters, and validates these ensembles to find the best performing model to be returned to the user. Most popular models are available in this library, but we have limited the model list to a subset that we've tested to optimize for speed, accuracy, and reliability. Our other supported provider is the DataRobot provider, which we've talked about a bit already. The DataRobot provider works similarly. You pass a simple SQL query to kick things off, and a lot will happen behind the scenes for you. It automates the training of dozens of models of various architectures and algorithms, including things like LSTMs and XG-boosted trees. It then returns the best performing model to the user based on over 15 validation metrics. DataRobot is capable of using cloud computing and parallelization techniques as well, which can help you train more powerful models in less time. And it also includes an informative UI. If you're a curious data scientist, you can sort of peek behind the curtain and see what it's done, what models it's trained, what models it prefers, the validation metrics for each model, and you can watch the progress of your training as well, which can be quite useful. This is just a quick look at the UI for DataRobot. You can see a long list of models trained. You could scroll down for even more. It also has validation metrics included and a drop down for more validation metrics. And on the right, we see that it's completed, but oftentimes this will give you progress of where your models are in their training and validation, which can be quite useful to look at. And this is only a single tab of the DataRobot web UI. There's a lot more information here to explore if you're interested. So if we boil down all of that provider information into a simple comparison table, we can see that both providers offer a selection of popular and powerful models and several validation metrics to gain insights from. In addition, both providers automate training and prediction with just a simple Iris SQL query. Where AutoML differentiates itself is by using an ensemble of models, and importantly is included fully with IntegratedML at no extra cost. DataRobot provider requires a license to be obtained through DataRobot, but does offer a very informative UI, parallel and cloud computing capabilities, and exhaustive feature engineering, which can be quite useful to get a good model. So let's see what we can do to apply this to a real-world problem. We will explore the future predictions with the Hungary chickenpox case dataset. So this is a spatio-temporal dataset, and it provides us with weekly chickenpox case counts for each of the 20 counties of Hungary across approximately 10 years. We're going to focus on only 4 of these counties so as to not crowd the slides with too many tables and charts and plots. Producing forecasts with this data, you could see how this might be useful to a hospital or a clinic who's trying to make decisions about future demands on staffing and equipment in the coming weeks. If they knew how many sick people would be coming in, they could make better decisions that would benefit both the business and the patient. It's also important to note that this data is highly seasonal. We talked about seasonality a bit earlier. We see peaks every winter with the case counts spiking up in the winter, which is sort of expected and similar to how we expect cases to peak for things like the common cold and flu in the winter as well. So here we have a visualization of the data. You can clearly see a yearly seasonality in all 4 counties. I'd like to point out that Budapest, the blue scatter plot and moving average line, has much higher peaks than the other counties, likely due to population density. And we can also see, though not as obvious, that Fejér it reaches its case count peak a couple of weeks earlier than the other countries on the average. And I only point that out so that we can remember that later when we make predictions to see if we've captured these kind of behaviors. So we want to make forecasts with this data. And luckily, the syntax for these queries is rather simple. We start with a create model query. So we include the name of the model we're training. We're going to name this one Hungary 60. We include a list of the columns or channels we'd like to predict. Here I've used a star to indicate that I'd like to predict every channel. And then we have this by clause where you pass your date time column as well. And then you finish it with from your, and then you put the name of your data source. And we also use this using clause here to pass extra information. There's a few options here, but in this case, we request to make predictions 60 into the future with forward 60. Then we follow this model creation with a simple train model statement. This will kick off all the training processes under the hood. And finally, once that's finished, we can get our 60 weeks of predictions by using select with predictions and the model name, followed by the usual things you would use a select statement for. You might put like a select list and then from your data table as well. And from this, here I've included the select with predictions again to keep it in your mind. So we input, the data on the left is sort of what we input. That's the from in our select statement. We had 522 rows, each being a week, and 4 columns of case counts. And the shape of the output here is 582 by 4 because we've added an additional 60 rows of case data as predictions. And here we've just used a snapshot of the intersection of the training data and the new prediction data, as that's why it starts at 5:35 or 5:15 and ends shortly after. But it would be better to look at the visualization here. In blue, you can see the actual county by county chickenpox case data. And the line is the moving average of it to make that a little bit easier to focus on. In orange, you can see the 60 weeks of predictions for each of the counties. To the naked eye, I would say it looks pretty good. We can see the seasonality pattern. We can see the seasonality pattern is captured well. And we can also see Budapest is projected to have much higher case counts than the other counties, as we expected, while Fejér is predicted to reach its peak case count a few weeks earlier than the other counties, which follows the trends we saw in the past data. But how do we really know? I mean, it looks great, but in my opinion, it looks great. But how do we actually know? How do we quantify if it's actually any good? For that, we have validation. So for every provider supported, IntegratedML will generate 3 validation metrics, all with a single simple query. That's just validate model followed by the model's name. And then everything else happens without you thinking too much about it. Each of these 3 metrics provides a different perspective on the model's performance. And they each have their own strengths and weaknesses, so you can get a holistic idea of how well the model's performing. The root mean squared error is on the scale of your training data, and that's useful for in our case, like on average, how many chickenpox cases am I off by each week? The mean absolute percent error is normalized, so it's much easier to compare one channel against another if you wanted to see how well is my Budapest prediction doing against my Fejér prediction. You could easily compare the percentages there. And then we also have mean absolute percent error. Oh, sorry, I just said that. We also have median relative absolute error, which compares your predictive model with a naive solution. Here we're looking for numbers less than 1, which means we're doing better than naive. And that gives the user a good idea of the strength of this model while also offering good outlier resistance because we're using medians. And each of these metrics is obtained using cross-validation. You might be familiar with cross-validation in traditional machine learning. This is a little bit different. In traditional machine learning, we sort of make these folds and we shuffle them around and do different training. We can't shuffle data around in time series as easily because we need it to be sequential. We need the time to be in order. So instead, you will take a subset of the training data and do a small test set after. And then with each split, you'll expand the training set. And then ultimately, you'll average together your validation results for each split to give you cross-validation metrics across each prediction channel and for each metric type. So let's take a look at the syntax we would use here. We start with a simple validate model, Hungary 60, which is the name of the model we defined earlier. This generates the validation runs and metrics. And then we can use a select statement to view the validation metrics table, which will include all applicable metrics in a single place, which is really nice to find and compare and to look at. And we'll zoom in a bit on a particular county here. This is the Borsod County, and I'll point out that the RMSE here is around 30, meaning our predictions were off by about 30 cases each week. And if we want a different idea of how we performed, we'll look at the MD Ray here. The value is a number much less than 1, which means our model performed much better than a naive solution. We can conclude that this model would likely be of value to someone looking to predict the future chickenpox cases in this setting. Thank you.
Cool.
Here you
go. All right, that was really cool. Love it. All right, so yeah, just gonna wrap up and talk about kind of where these things are and what we're doing overall with our plans. On the left, kind of near-term things. We just talked about time series modeling. We have an early access program now. And soon we'll have H2O provider support. So the early access program, please sign up if you're interested at all. It'd be great. We can just kick the tires a bit. It will be released with 2023.2, which I think we're expecting to land in July at this point. We also have our cloud offering now, which has a user interface to use IntegratedML as part of the cloud offering. That's been released, that's out now. And we will be adding to that the AutoML and data robot providers in the future. So a little bit farther out, kind of managing trained models across instances. So this is a situation where you might have a dev and then a staging and a production environment. You can't, at this point, export models from one iris and put them into another instance or save them out. You have to retrain them. So it's a limitation for a lot of production use cases. So in this, for that we're working on it. We're going to have that out soon, but it's definitely not scheduled exactly yet. We also talked about the model explainability. That's in the hopper, dev done. It's going to be released soon, but we're not sure. It won't be 23.2. It'll be after that. And also, we want to do more with the kind of the model ops. As I mentioned, taking models out of one instance, shifting them, putting them into another instance. That's model ops, really. I should put that in there. But tracking the data and the model drift is something that we could do a better job at, or we could provide some support for by snapshotting your data, being able to tell when it changes and detect those kinds of things. Detect when your model is likely to stop performing well. Often there's a lag. You know that the data is shifted and you're not sure when it's going to really impact the model performance. And so there's some tooling that we'd like to provide there. And we're open to suggestions, of course. I mean, this is something that anybody that has a burning desire or need to do something in particular, please talk to me and we'll see what we can do. So with that, we'll just wrap it up. And here's the people who were talking today. Reach out anytime. And we'll take questions. Thank you very much.